Thank you very much. It's a great pleasure to give this talk. It's a great pleasure to be across the Atlantic, if virtually, for this talk. And some of you may know I am from the Department of Physics and Astronomy, but also Department of Mathematics at Howard University. I do have an affiliate position, but I am predominantly a physicist. I have been working in mathematical physics or physical mathematics, maybe some might think of it. So I understand that most of the audience are mathematicians. Therefore, I beg some indulgence. Maybe my mathematics is not going to be as rigorous, and definitely the point of view is going to be a little bit different. For physicists, we generally gather evidence and put together a way of doing things rather than starting from some axioms and deriving things. So this is going to be more of a bottom up, as they say in America, rather than a top-down approach to the topic. That said, much of the research that I will be reporting today has been done with Per Berglund, and the papers are going to be mentioned during the talk. So here is a little playbill of what we're going to be discussing today, kind of coded here in musical notes, but I wanted to quote Xingtun Yao. I was a postdoc for Yao back at Harvard many decades ago, but as a physicist, I had a mathematician boss, and we always had kind of strained discussions of how to argue something or how to prove something. And this is a direct quote of him to me. Ultimately, it doesn't matter what it's called as long as there is substance. So I hope I will convince you that the investigations that I'll be discussing here do have substance. And perhaps then the mathematicians in the audience can provide the other point of view and perhaps more rigorous proofs to the things that I will report. Now, this is a very quick sort of introduction. What is it that I'm going to be talking about? So, Clavier manifolds have been constructed for quite a long time, several decades by now, and the famous quintic in P4, or the quartic in P3, the K3 surface, cubic in P2, which is a torus, and why not? Let's just go down to 0 dimensions. That's a quadric in P1, which is 2 points. So that seems very innocuous, very simple, very straightforward. And in fact, you realize, well, 2 points in a sphere, I might as well also describe 2 points on a torus, or as a matter of fact, I could be describing 2 points on any genus Riemann surface. So what should be so difficult in constructing Clavier manifolds inside manifolds of general type? So I will be deeply rooted in some of the things that have by now been kind of thought of as prehistory. And this is a quick slide of kind of the framework within which I'm working. The constructions that I'll discuss have to do with complete intersections. And so a complete intersection is the zero locus of some well-defined polynomial. And then you intersect several such zero loci, and all of that is defined in some nice enough space, in some well understood space. So here are these hypersurfaces, this sort of fracture xi, and then on each of these hypersurfaces, the zero locus, each of these hypersurfaces, the zero locus is defined as a section, more generally, not a function. There are sections of some line bundles, curly Li. And the nice ambient space here typically meant originally when we started this sort of construction, these meant projective spaces. They were generalized to weighted projective spaces, then to toric varieties. Presumably there are more general cases. And in the analysis of all of these spaces, what we generally use are two sort of tools. One of them is how to define germs of holomorphic functions on the subspace. Well, you use something called a causal resolution, where you use the dual of that line bundle whose section you're using, whose zero set of a section is that hypersurface. And in this linear mapping here, the initial map here is provided by just multiplying with that same section. That same sort of multiplication construction is also used in the adjunction theorem, where the tangent space of the submanifold is embedded in the tangent space of the one bigger space, so that nice ambient space that we're starting from. And then the map is this sequence of mappings is extended into an exact sequence. This then provides the normal bundle, and the normal bundle actually is that line bundle that you're using. So as long as you're dealing with the sufficiently nice ambient space where you know enough such line bundles and you can construct their sections and work with those sections, these kinds of calculations are doable. Now, we are going to be interested predominantly in smooth varieties, or what that means is that the defining equations have to be transversal. Formally, that means that the derivatives of those sections, the wedge product of those derivatives has to be non-zero, so there has to be a well-defined sort of normal bundle at any point of that intersection of the hypersurfaces. And so the fact is that this wedge product of the Fs shouldn't vanish at the intersection of those hypersurfaces themselves. So it might vanish somewhere else, but not on the subspace that we're interested in. That's generally defined as the transversality. And I'm going to work mostly with this kind of algebraic condition rather than being concerned with some sort of maybe functional aspects of that. And finally, I'm interested in Clavier manifolds, which means that the determinant of the sum of those line bundles, which gives me the anticanonical bundle. This is true for complete intersections. There are generalizations when the intersection is not complete, but I'm not going to go into those generalizations. So I know how to construct the anticanonical bundle, and that one ought to be sort of just tuned to have the degree defined by that ambient space so that it matches the determinant of the tangent bundle there. So that intersection has then a trivial canonical bundle. Now, what is it that we want to calculate with this long exact cohomology sequences? Well, primarily we're interested in the Hodge diamond, but also this endomorphism valued cohomology. And so, roughly speaking, this slide then gives you the things that we want to know. And this is sort of a nice time to give a talk when I can say that the techniques of how at least this started being used back quite a few years ago. The book that says about these things is by now 30 years old, so happy birthday. Since then, however, there have been other things that were discussed and developed. There are computer programs, there are all kinds of other new tricks. I myself am the representative of one of those other things, the old dogs. But I just wanted to point out one other thing, that these constructions here are predominantly for constructing compact Calabi manifolds. But it is possible from these constructions to also construct non-compact Calabi manifolds. For example, there is a very nice theorem by Tian Yao that says if you have a Fano variety and you excise from it a Calabi compact submanifold, codimension 1, then the remainder is actually a non-compact Calabi manifold. Also, we very often use in string theory the fact that the anticanonical bundle on any Fano variety itself is a non-compact Calabi variety. So with that said, this is sort of the preliminary things, the kinds of things that I'll be using. Let me now turn on to a particular example that I'll be following through. So this is where we will start diverging. Maybe a mathematician would prefer at this point more axioms and tools of the trade. I will focus on a particular family of examples and then see what I can learn from that. So here is a kind of old-fashioned notation by now. I take a product of P4 cross P1, and I impose two constraints. So this is a complete intersection of two hypersurfaces, one of degree 1m, the other one of degree 4 and 2 minus m. And for this one, the numbers here, 286, 168, denote the 2 is the dimension of 1-1 cohomology, 86 is the dimension of the 2-1 cohomology. The Euler number is calculated like so and given at the bottom. And I want to remember that although the initial construction here is within algebraic varieties, so in the complex category, there is a real manifold that underlies that complex variety. And so the Betti numbers given here, they pertain to the smooth real model. And there are ways of deforming the real variety much beyond what is accessible to the algebraic variety. So there is also another aspect that you will be much more familiar than I am. Causal manifolds can also be thought as symplectic manifolds with some maybe specially chosen symplectic structures, and there is a whole another way of approaching these manifolds, and this will come into play later. Now, let me analyze this in a sort of iterative way. First, I'm going to impose this first constraint, the P constraint, the degree 1m constraint, and then I'm going to apply the second constraint. So I construct this sort of layer by layer. The fact that degrees add up to 1 plus 4 is 5. That's the degree for P4, and m plus 2 minus m adds up to 2 for P2, regardless of what m I choose. Yes, I know you are probably wondering now, well, how big can m be? We'll see in a minute. That adds up to the fact that the first Chern class of the intersection is 0, so I'm constructing a Calabi variety. But let me look at the first hypersurface first. And this defining equation of degree 1m will define a space that in fact turns out to be closely associated to what are called Hirzebruch surfaces in 2 dimensions. So we're calling them more generally Hirzebruch scrolls. So this FM is a Hirzebruch scroll. There are many different definitions, how you may think of it, but I'm just thinking of it as this hypersurface. And I'll be a little bit more detailed about that in a minute. Next slide. But meanwhile, let's see what kind of topological invariance can we calculate about this hypersurface and also the intersection with the second one. I can calculate the Chern class, and this is done for the entire intersection here, but of course you can also do it just for the first hypersurface. And you find something interesting, that when you evaluate this combination, J1 and J2 are the hyperplane generators from one and the other projective space. When you calculate the cubic product of this evaluated on the intersection, you always get a dependence on this particular hallmark combination, 4b plus m times a, where m is the twist, this m number over here. You get the same when you evaluate against the first Pontryagin class. And in fact, it can be shown that any other Chern evaluation, so take any Chern class of suitable degree against the suitable power of this combination of the 2 generators, and you always get a function that only depends on this particular combination, which proves that in fact there is a basis change. You rescale one of the generators by a multiple of the other, 4 times the other, and you can show that a scroll of twist m is, as a real manifold, diffeomorphic to a scroll of that twist number m being reduced by multiples of 4. So this is a diffeomorphism shown by CTC Wall many, many decades ago. And so as real manifolds, those hypersurfaces with m's differing by multiples of 4 are in fact the same. So let's look at the first few one. M equals to 0, equals to 1, equals to 2. Everything seems to be nice. But then when you hit 3, well, it would mean that you need to use some Laurent type of section, some rational section. And by the way, the mention of rational sections here may sound like what I saw Alexander published recently in a paper, Laurent polynomials in mirror symmetry. The subjects are different and the types of the Laurent polynomials are different. So there might be some overlap with his work, but I'm not quite sure at this point. Definitely at the outset, they are different approaches. So let me look at how do I construct such rational sections? Does that even make sense? Well, on the original ambient space, projective P4 cross P1, there are no such sections. They are not holomorphic. They have simple poles. They're, well, meromorphic sections. But once I look at that first hypersurface, then actually there are plenty of such sections. In fact, there is 105 of them. This had been pointed out by the collaboration listed here. Lara Anderson and James Gray were the chief physicists in that collaboration. So that was back 7 years ago by now. And then Per and myself ended up looking at it a little bit differently from a different point of view and realized that, well, yes, they were perfectly correct. So once you impose that first hypersurface, all of a sudden there is a broader set of sections that you can construct, which are perfectly holomorphic. Let me describe that just a little bit. And this is arguably from a physicist's point of view. So the point is that after you've imposed that first hypersurface, sections on that hypersurface can be constructed from sections or functions or other kinds of objects on the big ambient space, but as equivalence classes, because you're always at liberty adding a multiple of that section where you are now on the 0 set of that section. Since you're adding multiples of 0, that's always possible. So in fact, let's look at Hirzebruch's original 1951 choice, a very simple section, that first degree 1m equation. And that's what I will call the Hirzebruch scroll. Corresponding to that, I can write a very specific section of this second type of degree 4 and 2 minus m. It looks like this. It's some kind of a cubic. I have plenty of cubics to choose from. And this is one possible option. This is not all 105 of them, but this is one class of them at least. So what happens now is that, remember on P1, where that's really just a sphere. You have two hemispheres, two patches that you can cover the projected space by those patches. And on one patch, you choose the multiple of this P section to be chosen with lambda equal to -1. And if you just add up all the terms, you see that all the dangerous denominators have canceled out. And on the patch where y0 is non-zero, this is a perfectly nicely defined holomorphic function. On the other patch, you of course do the opposite choice. And so as a physicist, I will say, well, this is just like what we call magnetic monopoles. Garbagnati and Van Heemen have shown in this paper that this is in fact very well defined. There is a so-called scheme-theoretic generalized complete intersection that one can define. And basically these two patches are literally patched together using the Meyer-Vietoris sequence. And so everything does have a very good mathematical description. I will nevertheless follow my physicsy intuition here. So let me look at this family of equations where the original one on the left-hand side, that's Hirzebruch's original choice. And then I can deform it a little bit, and I'll be exploring what kind of deformations exist and what do they end up producing or giving me. So the central member where all these deformations are tuned off, that's just the Hirzebruch scroll. And you may remember for the Hirzebruch surface, there is this exceptional divisor in it. And indeed, you can find an exceptional divisor in these higher dimensional Hirzebruch scrolls also. And following Griffiths and Harris, I'm going to call it the directrix. So the directrix has degree matching this 1m as 1 minus m, and then it has this maximally negative self-intersection. So in our case, if this is Pn in n dimensions, I'm primarily interested in fourfolds because then the Calabi threefold in it is going to be a three-dimensional space, but this can be done with arbitrary dimensions. So this is how that directrix looks like. By the same argument from the previous slide, this is going to be have a holomorphic representative on every patch of P1, and then you can put them together by the Meyer-Viatori sequence. So I'm just going to write it like so, leaving this lambda to be chosen plus or minus 1 depending on the section. So this is one construction we can explicitly do to verify we're indeed working on this Hirzebruch scroll. The other calculations that we can do for the hypersurface, that Calabi hypersurface in this Hirzebruch scroll, is we can calculate what are the sections of the anticanonical bundle. And indeed, when this epsilon is 0, you get extra sections. You can also calculate the number of sections in the tangent bundle of the scroll. And when these epsilons are 0, you get extra members. So this curly theta here is the step function. M has to be at least 1 over here. M has to be at least 3 for extra sections to appear. You can, of course, also calculate the higher cohomology. And in particular, there are non-zero 1 forms in both the anticanonical and the tangent bundle. And indeed, these purple terms are perfectly matching. And if you deform, if you now include some of the deformations, then 1 by 1 or several by several of these are going to vanish from the cohomology. Loosely speaking, your defining equation here becomes more populated. There are more terms in it. So when you go back to those calculations with the causal sequence and the adjunction map, there are going to be more terms that are mapped one to another, and they are canceled out from the kernel and the co-kernel. So that's roughly how the mechanics of this calculation works and why this is true. And so by the time you go to the maximally deformed version of this, then you're going to lose all of these purple contributions, and you go back to the original, just the black numbers given here, which, by the way, perfectly agree with Sage calculations and such more modern computer calculations. But along the way, as you deform little by little, we're going to find all kinds of other toric varieties in this process. So I just mentioned toric varieties, but there were no toric varieties to see so far. So let me show you how I can go from the projective spaces to toric varieties. And I'm going to omit a few little tricks here that one does, but roughly speaking, you do the following. So first of all, there is the defining equation of that first hypersurface, the one that defines the scroll. And it's a simple enough hypersurface that you can solve for either x0 or x1, depending on which patch you're working on, where the denominator y0 or y1 is non-zero. And then the other coordinate can simply be replaced by that directrix, the one section, that the rational section that I gave before. And the other coordinates, just leave them as they are. The by degree from the projective spaces gives you a set of charges, as we physicists would call them. And so this tabulation lists my new coordinates. Notice that I omitted the section that I'm setting to 0. And indeed, if I check the Jacobian of the transformation, this is just a change of variables for me as a physicist. So if I calculate the Jacobian of that change of variables, it's a constant, even though that directrix was a sort of strange looking section. But the Jacobian of transformation is constant. So let me just plow ahead and use these new coordinates. And I'll discover that they are actually so-called Cox coordinates in a toric description of this space. But what do I want with these coordinates? Well, I want to construct some defining equations for that Calabi subvariety that I'm trying to define. And this listing of the degrees of some product. So I take x1, that directrix, times any one of these blue coordinates, and that has neatly degree 1, 0. So I can construct my tentative or my candidate sections. They all look kind of neat. They're simple monomials of this form. So choosing m to be 3, remember we are looking at that, the first of those cases where I need to use rational sections. If I substituted m equal to 3, the first couple of them would look pretty nice, but that last one is going to perhaps present some difficulties, because when m is bigger than 2, this becomes a negative power, so this last batch is going to give me rational sections. And generally speaking, we should not be using those in algebraic geometry. So the standard wisdom is, let's forget about those for the time being. But then you notice something patently obvious. Each of these other sections contains at least one factor of x1, that directrix. And so therefore, here is an immediate theorem, if you like, that all the anticanonical divisors in that Hirzebruch scroll with the twist bigger than 2, they are going to factorize. If they factorize, that means the zero set is no longer irreducible. It actually is a sum of 2 components, the red and this purplish one. And the intersection of those is actually itself a Calabi variety, but now of codimension 2. It's easy to show this just by looking at the degrees. By the way, I did not mention at the beginning, I will make a sort of PDF print of these slides, so some of these details maybe, I know the slides tend to be too dense. You can look them up later on. But the point is that this Calabi divisor turns out to be reducible, and its 2 components, one is the directrix, drawn here as this straight red line, and the other, which we then might want to call the complementrix, because it's complementary, that's this purplish line. The 2 of them, both of them are smooth, both of them are defined by transverse sections, but they intersect, and of course the intersection is singular. That singularity itself is a codimension 2 Calabi variety. We got to calling them matryoshki, and it turns out that several other mathematicians are using the same term for similar sort of constructions. And it turns out to be possible then to use these coordinates, as I mentioned, identify them as Cox coordinates of a toric variety. And indeed, from this matrix 2 by 6 matrix of degrees, it is possible to interpret these degrees as the Mori vectors. And from those Mori vectors, it's possible to, by some sort of reverse engineering mechanics, to figure out what is the fan, and in particular, what is the spanning polytope. I'll use this term fairly often. I found it in a textbook by Günther Ewald on toric varieties. It is definitely not used very often, but I find it nice. So the polytope mentioned here is not the Newton polytope, it's sort of the dual of it. It's the polytope that kind of encompasses, that combinatorially describes the fan of the toric variety. So that's this polytope. And notice that it is inconveniently not convex. There is a line that connects nu4 and nu5, and that is outside the polytope. Or if you like, think of it this way, that nu1, the vertex nu1, is a kind of saddle point on the surface of this polytope. So it's non-convex, and it turns out that these kinds of divisors that have 2 components to them, and the intersection itself is a Calabi codimension 2 subvariety. They are called Turin degenerations. And since the standard sections do not include anything with which we could smooth those singularities, it's regarded as unsmoothable. All right, so I just wanted to summarize a little bit that construction that I gave before. How do we construct those rational sections? So here is a sort of construction, how to do that. You start with your defining equation, look at suitable multiples of that defining equation, and look for such terms where each such multiple has two parts, and in one part, only one of the two P1 coordinates appears in the denominator. In the other part, it's the other of the two homogeneous coordinates that appears in the denominator. And then you, however that polynomial looks like, you flip the relative sign between these two. So that's the construction, and I'll give you a very simple Mathematica code here that does this construction for the Hirzebruch surface in 2 dimensions and with the twist equal to 2. So when you list all these polynomials, obviously I'm limiting this listing on one and the other side, focusing in on the things that will be interesting. Here is the one that I would like to choose. So this one does have one summoned where I have y0 in the denominator and the other summoned with y1 in the denominator. The one adjacent to it, left and right, I have mixed ones, so I drop them. The ones, if I go too far to one side or too far to the other side, it doesn't have denominators of both kinds. If I multiply this by some powers of y1 over i0, I will get algebraically dependent but viable sections. So I'm not interested in those because I can always reconstruct them from this initial one, and everything else drops out. So this construction indeed provides the one and only directrix that there is in this Hirzebruch surface, and it has the right degree. This is the exceptional curve of in that F2, the Hirzebruch scroll of twist 2. You can also think of it as the blow up of a singularity. So that's why I call it the exceptional curve. So how about if we start exploring a little bit what happens near? So let me add a little deformation to that initial defining equation. So it's no longer exactly the Hirzebruch scroll, it's a slightly deformed version of it. You can go through the same analysis, find whatever directrices that you can find. I hope that's the right way of making a plural out of that word. And here are the two that are independent of each other, algebraically independent. I can use the original section and the two directrices and the remaining coordinates, find that the Jacobian is constant. Following my nose as before, I reconstruct the toric variety and I find something interesting. The deformation has ended up smoothing or kind of making the toric variety a little nicer. Originally, nu1 was a saddle point kind of non-convexity in the polytope, where adjacent to it were 4 edges and alternatingly 2 were convex, 2 were concave. Here, 2 are convex, 1 is concave, but one of them became flat. So it kind of becomes slightly better. Let's explore this a little bit more, deform it a little more. I find the two corresponding new directrices. I check that the Jacobian is constant. I reconstruct the Cox variables, and from that I reconstruct the spanning polytope. And now that nu1, nu3, that edge that originally was concave, then flat, now becomes convex. So this is indeed the general procedure, that if you keep deforming this original section with which you're defining the first initial hypersurface, you get better and better models. And here is a particular deformation where ultimately when you go through this process, you actually end up with a spanning polytope that turns out to be perfectly nice and convex. So that means that my deformation family of all such sort of degree 1, 3, or 1, 5 in this case, hypersurfaces in P4 cross P1 contain all these different kinds of toric varieties, some of which are non-convex, and the generic one, sufficiently generic one of which turns out to be convex and describes a Fano or almost Fano, or there are some other adjectives you can use here because it does have this flat edge in the spanning polytope. It's not completely strongly convex, but nevertheless, it is a Fano variety. So let's go back now to our original picture where we had this standard wisdom was forbidding us to use these sections. Per and I decided, well, what happens if we do use those sections? One quick conclusion is that, look, those sections do not include x1. And so if I put a sufficiently small parameter in front of them, locally around what previously was a singularity, I end up getting a smoothing. So this is actually a way how to smooth those previously thought to be unsmoothable Turin degenerations. But of course, the price to pay is that you have to use a rational section. Well, let's embrace those Laurent terms. After all, we all know about L'Hopital's theorem. See if we can somehow figure out if these singularities that you've introduced by the pole, are they perhaps somehow removable? So let me just describe a little bit one way, our physicist way, thinking about it. So let's realize the following, that here is a simple, very simplified sort of choice of that defining section. And it has a single x4 appearing in the denominator. Okay, so near x4 equal to 0, of course, this is ill-defined. And can we make sense of this? Well, away from that x4 equal to 0, this is a perfectly well-defined function. I can set it equal to 0. But more importantly, once I set it equal to 0, at least one of these coordinates I can express in terms of the other one. So let me pick x2. In fact, x2 squared has to equal to this. And so away from the pole set, this is a perfectly good way of defining the 0 set. And then I look at the limit, preserving that x2 equals to this particular function, the square root of this. And I can define the approaching to the to those putative singularities, instead of approaching them in arbitrary way, which we know is not well defined, but approaching it in this way, I can ensure that the section always vanishes. This is just like when you're trying to define sine x over x, when x tends to 0. Now, I know sine x, of course, is not part of algebraic geometry, but here we have a very similar situation, at least. So as physicists, we thought, okay, this is a meaningful way of defining these kinds of hypersurfaces. And then those of you who are much more adept at blowing up, blowing down, and those kinds of things might also try. The problem is that we don't understand how to define this particular point, this intersection of the pole set and the 0 set. Well, how about go back to the ambient space? It's a very nice space, P4 cross P1. Blow up that location enough number of times so that the pole set and the 0 set, the proper transforms, are separated, then fill in the point in the 0 set, and then blow down. So is it possible perhaps to more rigorously define it that way? So while I was talking to some mathematicians about can this be done this way, two of our colleagues pointed out that there are actually completely different ways of talking about such spaces. And we thank Amin Gholampour for pointing out that Severi had introduced virtual varieties over 100 years ago. By now they're called Weil divisors. And so instead of looking at a Laurent polynomial like this, using a separate rational section, just think of it as a ratio of two polynomials, corresponding divisors. Formally, we're looking at a difference of those corresponding divisors, so that's the Weil divisor. And I don't know enough about how to calculate Hodge numbers and those kinds of things, cohomology calculations for such Weil divisors, but that's why I denoted here this is work in progress. In general, we'd expect contributions from the denominator to subtract from those of the numerator. Independently, also we thank Hal Schenk for putting us in touch, intermediary touch with David Cox, and David Cox found this particular mapping. If you just replace the coordinates in my simple example, x2, x3, x4, with these particular coordinates, z1, 2, 3, then what looks like a Laurent quintic turns out into a perfectly ordinary Desic 10th degree equation, but in a different weighted projector space. Okay, well, subsequently, I managed to generalize this for all of our Hirzebruch scrolls and then for the anticanonical hypersurfaces in this. So this is definitely not a fluke. It can be done algorithmically, at least in one way. But again, in order to describe our original Laurent quintic and to calculate Hodge numbers and those kinds of things, you would have to contend with this mapping, which involves square roots and powers, square and higher roots and powers. So generally, I'll be looking at some sort of a mapping that describes a desingularized finite quotient of a branch multiple cover. All of that belongs to standard algebraic geometry, but it's a little bit too complicated for me. So I'm going to skip these additional ways of analyzing what I'm talking about and just try to describe to you what is it that we did do. So go back to this model that previously had a non-smoothable Turin degeneration, which is now smoothed by these Laurent deformations, and see if we can make this sort of stick, if we can do something more substantive with this. So first of all, let me describe some of the combinatorics that goes with this. Here are my monomials. I'm going to look at a sort of two-dimensional proof of concept. So now I'm back in 2 dimensions. This is really the Hirzebruch surface, not the higher dimensional scrolls. And so I'm looking at actually describing tori. But here are the monomials. I can plot them out. Some of you will recognize that this is kind of building towards something like a Newton polytope. But let me just go with the flow here and plot out these monomials in a certain fashion. And here is the second sequence of monomials, and here is the third sequence of monomials, the ones that are going to be rational, that are those Laurent monomials. So this is the set of points, and just to make sure that all of this is working properly, there should be a procedure where I go from the functions back to the space on which they are defined. So this is done usually with this polar construction in toric geometry. But I need to work here with polytopes that sort of the outline of this is evidently not a neat convex polytope, so we called it a transpolar construction. How do I do that? I decompose a polytope that you will see in shortly. I decompose it into components, into faces, facets, and then facets of those facets, so all the faces, and I look at only the convex of those faces. And then I construct the polars of each of those faces. So here is the dual origin, and then I look at a particular facet, which is convex. I find a corresponding dual vector. Another facet here, the corresponding dual vector, another one. Then I look at lower dimensional faces, so just vertices in this case, find the dual of those, and again, and again, and again, and lo and behold, of course, I reconstructed that non-convexity, that locally concave component in that spanning polytope. And indeed, I can reconstruct the entire polytope by using this perfectly uniform or universal relation between the duals. When I have some two faces and I look at the intersection of two faces and then I take the polar of that, it's actually on the polar side, it's going to be a face that is delimited by the polars of the individual components here. So I just use that to reconstruct the whole object on the left-hand side, which is used as follows. I look at the top cones, one and the other, the intersection of those two top cones, ignoring everything else. The intersection describes the gluing, and that structure on the left-hand side gives me a poset of cones, and that structure is the fan. The fan defines the Hirzebruch variety, so this Hirzebruch scroll. I can do exactly the same thing on the right-hand side, sort of one of those convex cones at a time. Look at its adjacent one, look at the overlap, and notice that there is something funny happening on the right-hand side. There is this sort of flip-folded term. But that I can also use as a poset of cones, and that defines a sort of fan, or a multi-fan more correctly, and that defines some kind of a toric space also. Now, it's not a variety in the same sense as the one on the right-hand side, but it is a toric space. And this transpolar construction, defined like so, is perfectly, it duplicates. So if you apply it twice, you get exactly back where you started from. You don't lose any information. So the non-convexity here is perfectly encoded by this flip-folded sort of term. And I contend that just as the anticanonical hypersurface in the toric space on the left-hand side is a Calabi space, so is the anticanonical space on the right-hand side, and these two are mirrors to each other. So at this point, I need to, in sort of Star Trek speak, need to engage warp 10, because I need to cover some ground, but very quickly. So I contend that this construction is consistent with all kinds of other constructions that do that polar mapping. But the other thing that we discovered is that these kinds of flip-folded, for lack of a better term, of these combinatorial objects, they have been used for, well, 30 years or so, notably to construct pre-symplectic spaces. And then since 1999, they have also been explored by Hattori and Masuda and others who call these things multi-fans, the fan spanned by such a flip-folded polygon. There are lots of other constructions. They typically talk about symplectic structures in toric spaces, not necessarily varieties. And there is a notion that in a pre-symplectic geometry, the symplectic structure might degenerate at some small enough, mild enough, nice enough subloci. So something similar might happen with a complex structure on the left-hand side. Allowing for this, we're now going to very quickly just look at, well, can I construct mirror manifolds? And the simple claim is yes. If I use that left and right-hand side model, this is now in 3D. Over here you have the picture of that spanning polytope of a Hirzebruch scroll. Here you have the corresponding extended Newton polytope. And there are ways to reduce this, to reduce the number of vertices you're going to be using in a construction. And lo and behold, these are the possibilities. There are some color coding and underline coding. Let me just show what I mean by that. So the red coordinate, I'm always going to substitute by 1. This corresponds to blowing down that exceptional divisor in a toric description of the Hirzebruch scroll. And I will either set the coefficients, the underlying coefficients, equal to 0, or the blue coefficients. And I will set the blue coordinates equal to 1. So doing that, I obtain, by the way, let me just go quickly back to this page. That corresponds to these perfectly convex polytopes, Newton-like polytopes on the right-hand side, and the perfectly convex polytope on the spanning side. So going back here, these are the definitions that specify these choices, and I'm only looking at the corners. I ignore all those other points in the inside of those polytopes, and I can construct mirror models from that. This is using the fact that the degree matrix you assemble for the first monomial here, you look at the degrees, that gives you an array of degrees. You look at all the arrays, that gives you a matrix of degrees. If so reduced, it gives me a square matrix, and I take the transpose of that matrix that defines the action of these discrete symmetries. And that is exactly what we use to identify which particular model is the mirror of which particular model. So in this second choice, you have to actually divide by some Z4 and Z3 symmetries, for example, here. In the first choice, either one or the other, you need to divide by Z3, and that constructs the mirror models. So notably, these are deformations of each other, so we actually have a sort of generating machinery of what are called multiple mirrors. So not only a mirror model, but in fact multiple mirrors. You can do this for all kinds of other constructions. I just very quickly show you a bunch of these things in 2 dimensions, because then we discovered these are actually what Poonen and Rodriguez-Villegas call the generalized legal loops. And they have defined in a different way a combinatorial definition of a duality in their case. And the red and the blue excessively self-intersecting polygons here are extensions of what you would call the spanning polytope and the Newton polytope, and you can construct Clavier manifolds from these. But their construction only works in 2 dimensions, whereas ours extends it to higher dimensions. You can also identify, well, what happens if on the spanning polytope side you have some face that has degree other than 1. That actually indicates a type of singularity. And to resolve the singularity, you need to subdivide that face, which corresponds on the Newton side to chisel down the polytope. Well, what happens if that should introduce a concavity? Then the Newton polytope ends up getting extended. So you get these sort of self-intersecting types of polytopes in higher dimension. And lo and behold, you can find all sorts of other local kind of surgeries on the Newton polytope that can happen, like this substitution of a tent-like region with a hammock-like region, which introduces a non-convexity, and all kinds of other things with saddle point-like features and so on. So I'm not going to detail this at all, because I'd like to use the last 5 minutes just to give you some more of the benefits of what this sort of line of inquiry brings. But let me just point out that some of these constructions end up involving polytopes that kind of whirl around more than once. In other words, that the fan that you construct, that poset of mutually adjacent cones, the multifan, turns out to cover R2 or R3 or R4 more than once. And that winding number, as Hattori and Masuda call them, turns out to be the same thing as this holomorphic Euler number. So those are the kinds of spaces that we might want to include. Let me just quickly show what happens when you are looking at what physicists approach as the very small. So how does the geometry start looking differently from a physics point of view when you look at very small features? And this is using the GLSM, the gauge linear sigma model of Witten's. So this slide was geared towards describing, for a physicist, how do you find certain things called vacuum expectation values, whatever. For a mathematician, the point is that you reconstruct something that mathematicians call the second fan, or the secondary fan. So very quickly, just to show you that for the different twists for m equal to 0, Witten has originally plotted this secondary fan. It looks like so. Morrison and Plesser 2 years later plotted out the secondary fan for the F2 case. It looks like this. And by the way, as the dimension grows, instead of n equal to 2 for Hirzebruch surfaces, n equal to 3, 4, 5, and so on, this vector it changes from -1, 0 to, or -2, 0 to -3, -4, 0. For F1, it's easy to find what that interpolating secondary fan should look like. But then it is equally obvious how to construct the fan for F3, for F4. And anybody who has worked a little bit with toric geometry will immediately realize that this yellow cone here needs to be subdivided by exactly one subdividing vector, here with 2, here with 3, and so on. So in fact, the conclusion is that none of these secondary fans are equal. Remember that wall diffeomorphism that says that F4 should be diffeomorphic in n equal to 4, should be diffeomorphic to F0, while the secondary fans are nothing like. So this gives us one way of distinguishing in the complex category why these spaces are different. But actually, there is an exact calculation that can be done. Physicists refer to that as worldsheet instantons. Mathematicians would refer to that as the A discriminant. Let me just flash the result. You can actually find the exact closed form solution for that A discriminant. And yes, it looks quite complicated, but that's kind of the point. There is no way this formula could possibly turn out to be mod n periodic. In other words, this definitely shows that the Calabi models constructed in F0 are distinct from the Calabi threefolds in F4, in F8, and so on. So there's actually an infinite sequence of these guys. And for each of these, we can construct the mirror. Again, I'm just going to go very quickly through these slides because the story relies on what I mentioned before. And I'm just telling you, yes, it can be done. But along the way, as you do it, we can, on the mirror side, we can now look at the A discriminant in the complex structure moduli. And there you have explicit monomials, which sort of form a ring, but it's a residue class ring, so there is an ideal. You identify that ideal by just finding the relations among these monomials, such as f0 squared equals to f1 times f2. And modulo that ideal, you construct this variable that I called here beta, and you can indeed describe the A discriminant in terms of that parameter beta, and lo and behold, plot it in Mathematica, you get exactly the same picture. You can probably prove more than that, but for us, this was indication enough. So we said, well, how about we do it the other way around? So far, we looked at, let's call it the left-hand side model. We identified the Kähler forms there, and we looked at this sometimes called Horn uniformization. That particular A discriminant. On the mirror side, we looked at the complex structure. So how about if we do it the other way around? Well, there are many more monomials now, many more generators. The dimension of these moduli spaces are much bigger, but we'll restrict, we'll forget about those MPCP blowups, those inside points. We'll just look at the corner points of the those polytopes. And in that case, we can follow the same mechanics and reconstruct how does now the n-dimensional discriminant look like. Here are the formulas. They look different, but when you plot out the generators of the ring over here and the generators of the structure, you can find actually a perfect one-to-one matching between these two. The details will be shown up in a paper real soon now. So I cannot display those details, especially because I've just run out of time. So here is a quick summary of what I have kind of implied that we can do. These are all the calculations that we can verify for arbitrary m. M goes definitely higher than 2. We can also calculate Yukawa couplings with a little bit of trickery, and unfortunately we have to do it sort of case by case. Gromov-Witten invariance, not so much. There are some difficulties in calculating that, predominantly because we don't quite understand very well what is it that we are calculating. And on the mathematics side, there is the set of extensions that I kind of mentioned. So other than that, I showed you a sort of family picture, a deformation family picture, where the Hirzebruch scroll is in the middle. Those other kinds of toric varieties are in different kind of directions on the side, one way or the other, but they definitely include some of these convex examples. And here is the conjecture that we have, that in the convex model, of course, that particular Turin degeneration is perfectly nicely smoothable by algebraic sections, by regular, ordinary holomorphic sections. But in the central model, it is not. It is deformable, however, by Laurent deformations. So we conjecture that, in fact, those Laurent deformations are the epsilon goes to 0 image from the regular deformations in the regular case. And thank you for your patience and for allowing me to go 2 minutes over time.